1, 2, 3, 1, 2, 3, audio test. A, B, C, D. Ooh, I got a new gadget. It's not new. I just finally figured out which one works. 2, 3. Hi, I'm David Malloway, and we're here in Open Lab in Bryan, Texas, and I'm still not ready to create a full organized lab tour, so I figured I might as well at least log in and just give an update on lots of things that are going on. This will include inclusion of steel rods in the structural members that I think are prime for building all different things, including the lab station's equipment and the projects that we create in the lab. Simple bracket, wall mounted. Oh yeah, that's over there. Rag chute 1 and 2. Cardboard rack design. I think you will like that one. And stitching. Okay, let's start. Oh, before those bullet points, I might as well clear this desk off. And what is this? This is part of a high pressure water pump. And this is my reminder that I am still itching to get my hands back into machined billet, aluminum and steel parts, CNC stuff. I love all those things. But for right now, okay, look here. We have, this is a consumer grade, but nice gasoline powered water pump, and we're just looking at the insides of it. We could do hours and hours of learning about manufacturing and design just from this part alone. I got it out yesterday because I was looking at the choice of screws. So this is in the background, and probably I'll have more content in the future. What types of screws are we choosing for machine screws in different applications? And you'll notice I don't very often use the socket heads, and these cost a little bit more than the round heads you'll find in these extrusions and most of my parts that mate 3D printed plastic and metal. Anyway, this machine is just cool, and there's no water in here. The water flows in between these three orifices up in the upper assembly. This sits on top, and these steel rods drive water to go pushy. So you get this very curious action where you can push one. It's like a whack-a-mole. Push one and the others go down. And that is the corresponding to the spinning of this. So the inside of this assembly is really cool. Can't pull it apart now because the springs in there make it challenging to put it back together. So I'll put this away, and that will remain on the display shelf until later. Look, I'll push here and you'll see it spin. Yeah, that is just so cool. Very precise machining involved in this. You guys are going to help me clean up. So what is this thing? That's a hygrometer. Temperature and humidity measured together. This is part of the process of, we're doing some benchmarking. I just created this 3D print yesterday, and we're going to find an off-the-shelf recommendable hygrometer. These are 4 for $10, and they seem to have more consistent consistent reporting than this previous brand. They're both Chinese no-name brands, but before I start talking about them in a video or a project, I wanted to choose one that is worth buying, even if it's a low cost. What is this thing? This is for DIN rail. The DIN rail ships in 1 meter lengths. That's the price. The length that will get you the most value, bang for the buck. And so it comes in a nice rigid cardboard tube like this one. And I pulled out the last one of those to do some mock-up and see of how much space do we get if we want to mount things up overhead instead of down low. Previously, I had a rack about this profile for running individual tests on electronics, but there ought to be, here it is, there ought to be a bigger space where we can hook up more things and maybe also include a shelf. And so this volume in the lab where we are not using the space, we can use some of that. I want to keep some space clear overhead so that light can still shine across the room and good filming happens. But in some area, Maybe I want to have a specialized light mounted and so forth. Oh my goodness, listen to me saying maybe this and that and so forth. No, I can be more specific than that. We want to have this capability, some amount overhead at the station. This is going to be, I think, just as important as the woodworker has hammers and chisels ready to go, or we may want to, there are several tools like pliers that always wind up right here on the magnet. But for a multidisciplinary type of environment, there are some electronics that always need to keep on appearing, such as a 12-volt DC power supply is going to appear in almost half of all the projects, and having a modular distribution of power will appear over and over and over as it has in the past. And so those things can get permanently mounted above the initial need, nearest. The need that I wanted to address most urgently was to get pens and a couple of screwdrivers. So you may see down here, I had just screwdrivers and pens that I'm retrieving dozens of times per day, mounted down low, and I want them within arm's reach wherever I am at this table. And so we have the modular, this is called open box, the electrical box from which I've created many template designs that you can print and slap on there. For this one, it's a pen organizer. And for that pen organizer, I think I want to have it right around this area. And so at some point, either a frame will go on this big table or a frame will go on the toolbox like this one. And this is the form factor of toolbox that many people have. It's sort of like the bare minimum entry point after we have a little handheld toolbox and somebody either in a lab, a mechanical space, or in their living room, wherever people are doing projects. At some point you invest in a toolbox, and this is the size and shape I think that I see most often. So if we design a module that goes overhead and mounts to something like this, and it has versatile mounting, then we have a solution, a starting point solution to turn the toolbox into a multidisciplinary tool station for loads of different people. And the questions are, what materials will it be made of? That brings us to 2x4s, extremely common for framing up simple tables and things. Then we have the DIN rail, which does have some structural capabilities, but it's not rigid enough to be the frame. Then we have the aluminum 3030, which is rigid enough to be the frame, as you would find in these tower type bin rollers. And those are strong enough, but they're pretty expensive. So the question is, what's the value for choosing the 3030 extrusion and having this cost, let's say, 6 times more than wood? What's the value? Okay, one, it looks pretty and it looks modern. That's nice. But what we're really paying for, I think, is the features, the ability to bracket on all 4 faces and have it so precise that this can be used as a datum from which to build the other elements. It's precise enough that then when you make a CAD model of this, if I make a CAD model of this table, I cannot mount things and have the angle and the spacing within a millimeter, then the CAD model doesn't really serve its purpose. Versus this, if I design something that mounts to the rail and I need the millimeter of precision, I can get that. The model reflects the material in real life, even if you're building with hand tools. And that's what we're paying for when we upgrade from wood to aluminum. In my opinion, that's where we are. So if we don't need this precision for every single area, we only need it for some areas. This vertical beam could be replaced by anything. It could simply be like wood. That could just as well be the strength is sufficient and the mounting abilities. We would change that bolt to a wood screw and everything else could happen in the same way as the aluminum with wood. And then it's the whole design becomes accessible to more people. So the question is, where do we need, can we build with wood and this aluminum, or an alternative as however we choose? And the answer is yes, if we make some adapting components. And so then you have this revision 1 of a bracket that will take a steel round tube and mount it to the wood. Now we can have a frame that is partly made of wood, and then we use the steel rod when we want the same strength that the 2x4, but we don't need, let's say, this mounting surface. So the cost, let's say that the 2x4 is $1 a foot, even though it's less. Then we go up in cost to $2 a foot. If you need the steel rail, you get some properties, some accuracy that you wanted, like the precision is it agrees, but the but you don't get the datums that you would find on the aluminum. Okay, so precision and strength is here. Precision and strength and datums are here, and just strength for wood. This is how I'm comparing mentally what I'm going to build things out of. So, and then this one is precision and datum, and not as much strength, but still more than zero strength, such that in a frame like this we can say, hey, let's eliminate the aluminum here, reduce the cost. Let's say that the DIN rail and the steel both $2 a foot. We go $1 and then $2 for these two, and $3 for the aluminum. Now we can optimize. We have a general relative cost where the steel and DIN are more expensive than the wood, and then most expensive of all is this one. So what is this stuff, and why did I choose it? It's actually the everyday common, at least in the U.S., fence rail. It's called 1 3/8 inch, and it's a steel that is harder than the conduit we have shown in previous videos. However, the beautiful thing is I realized that this will cut. You don't need a hacksaw or a power saw. You can simply use that same circular tool that I've shown. It's a rolling, I'll come back with the name or add it to the comments or something. So it's easy to cut with a $15 tool that will last a lifetime. Wonderful. And it's silent. You could cut it at midnight, even if you have roommates. Okay, now we're gonna, this part's crushed. Anyway, this is made to be a structure versus the conduit is not. Let me grab that. Oh, I'll show you. Okay. Whoa, whoa. This is the 1-inch conduit, the largest. In my example designs, I've posted 1/2 inch and 3/4 inch conduit. This is the 1-inch conduit, which I was not intending to commonize at all, but I wanted to try it out last year. And it's a soft metal. It's soft because it's intended for the technicians to bend this to build out their installations. Both of these are galvanized. The fence, no, this is the conduit as well. 1 inch, so it's very American. I don't know where else they have these. I'd love to know who else has conduits with 1/2 inch, 3/4, and 1 inch, but those are trade sizes. Anyway, a couple millimeters larger than that is the fence post. And so in the past, I found these on the curb. Somebody just did construction and left these old fence posts. These are even better. The galvanizing is more severe, thicker galvanizing. So it'll go a long time without rusting. And if it does rust, we can refinish it because we're handling painting and sanding tasks in the lab as well. Ugh. So the size is 33.4 millimeters. And after measuring several variations, measuring one that's been weathered, measuring one that's new from different sources. 33.4 is very repeatable. That's excellent. And so they're not going after something so precise as we need, because the way they're fit together is through these, what do you call that? Anyway, they fit nesting inside of one another. But we're going to chop that off, and then we're going to treat it as a pure plain steel beam with a consistent geometry. And then when we make a bracket, I made this bracket such that it's a press on, slide on fit, where you get the friction. It has two diameters. This diameter of the tab, there's a better word for that. That one is matching 33.4 millimeters with some overbuild. And then I clear out the material. 3 segments of 90 degrees clears out the material, so it's only contacting in 3 regions, and then you get a really nice press fit. My fingers are getting cold. Going inside. So for this design, it was the fastest design possible rather than the design with every different feature. That way, we don't have control of the tightness of it, and the tightness of it looks like that. It's kind of maybe 2 hands is the minimum to get it moving, and some twisting is required, so it's nice and snug, certainly snug enough that 4 of these holding down, can you see that? 4 of these holding the 2 posts will constrain us vertically. If I put, I think, 50 pounds on the rack overall, these won't slide. And if I go above 50 pounds or I start striking and having impacts, then I'll need to change out that design. It could be made beefier. It could be made modular to where it has a fastener and it closes and clamps. That's and we have examples. So I've already published examples that give you a clamping around a round tube and an adjustable tightness. And then if the plastic itself is too weak, then this is a parameter. The thickness of this rib and the overall thickness here, all parameters, as well as the width. So how tall should you make this when you design this? Well, I just simply chose the same height as the 30-30 rail. I said, well, it's going to be about this range, but instead of giving an arbitrary value, I said it's going to be 30. So then if I want to use it as a bracket for this rail, we already have that solution built in. So for structural beams in OpenLab, we're supporting pine lumber 2x4, aluminum 30 millimeter rail, DIN rail 35 millimeters, and this round steel that I've introduced just here. And we want to have all of the basic construction brackets necessary to configure those in ordinary shapes. So that brings us to, all right, now we can bracket things at 90 degrees, and we should have maybe a bend, a joint. And so this is a joint that I may have already shared in the past, all right, and it's based on the same model as the joint for the extrusions. And it has a limited amount of strength, a certain amount that won't be tested until we have a specific use case. To use the use case, use the application to designate a desired strength. Call that application the standard or template or baseline, and then decide how much should we be able to push or pull on that. And so this is a design that I guess I wouldn't call it finished. I don't know if I shared it yet, and it's actually made in 2 parts. I'm gluing the part A to part B, and you can see the seam there. And I can't finish the design until we have that template application. So then we can have a strength criteria. So the cross section looks like this. The fastener, unlike the rails, the extrusions, we actually protrude into the steel, and we have to drill a hole in the steel. And this one is a threaded hole. There's lots of ways to do this. We don't but the threaded hole at least creates a reference of 0 degrees around this tube. From there, now if we want to have an upright element, then we need to know that we're making it upright from that line. And that line is invisible, and so there's actually several requirements that come together with starting to use this and making it practical. Pins can change out for steel or fiberglass. The whole thing can be made stronger, so raising the strength after we get an initial baseline is not difficult, and those possibilities are built in to some amount. The parameters will allow that to expand. Okay, now what is the fastener involved here? You're looking at one that is an M5 screw. It's a metric screw, 10 millimeters in length, and there's a little bit of a recess built into this plastic so that part of the function of these recesses is that you can do clamping of a plastic thing without needing you can adjust the thickness of this plastic, but you don't want to always buy a different length of screw every time. And so this parametric pocket is what it's built into most of my models that are like this, and the seat of the floor is defined against the base the surface, rather than just making the screw required to change every time I change the thickness of this. The screw will sit right there if we make this thicker, and then we can still inventory fewer screws and familiar sizes of screws. So that's M5, but maybe for the next version it should be M6. M6 is the size that the cost is very similar between M5 and M6. This is the box that I always open up starting a project that uses M6 fasteners. 12 millimeters is the one that gets used the most, and then I jumped to 16. So if you're gonna just purchase 3 different M6 screws to start doing projects, I would do 10, 12, and 16. And that's probably the reasons that demand other longer lengths are much more varying than the use cases for the shorter lengths. And since they're varying, now you have to make a lot more decisions in order to commonize the long screw lengths. And then at least the washers are so cheap they're almost free. I would recommend at least one thick style washer that gives you a beefiness, and one that's thin that can do its job as a washer but not take up too much space. And then you have the 3 different kinds of extrusion nuts, the kind that sit in and clamp. This is only used for 30-30 versus these ones. Once in a while they become used. These 3 are generally only used for projects that involve the 30-30, whereas of course the ordinary ones can be used for any different project. And so as far as budgeting a maker's budget, then this is still the starting point where if you were going to buy a pack. Okay, we covered the inclusion of steel rods, the simple bracket. Oh no, I didn't include this. All right, let's do this. 2020 extrusion wall mounted. Why does that need its own special bracket? Okay, there are many reasons you may want to mount an aluminum extrusion on the wall, but only a few reasons you may want to tilt it. And so I avoided making this bracket for a while and just tried to make silly adjustments on the hardware to get my angle tilted up. The problem I had to solve was these little fingers tilt down just due to gravity and the small slop in the assembly. And that's not okay because my hardware will fall down and these bins will break. And so I'm going to dismount one of these aluminum extrusions, and I'll show you how that works in case you want to use that. It's not yet published on GrabCAD. I'd love to know if anybody really needs it, then I will take the time to publish it. But initially I wasn't even intending to make it. So you have a bracket that simply grabs a hold of the 2020 and mounts on the wall. Simple enough. Minimum of 2 are required to mount. And if you choose more than 2, these are placed on the studs. So those screws go into wood. That's what makes them strong. And that is what allows me to just have 1 per bracket. And you might worry that, see, this long beam only has 2 as well. And I'm almost concerned. It crossed my mind to be concerned about the strength of the bracket, but I'm not concerned. And I'll show you why. I think I'll have to dismount one of these. So it goes in like this. You tilt it, and then you snap it. That last snap, I'll have to show it up close. Okay, the screw here is actually a Robertson drive or square drive. And so 4 sides is 4 is orange. So that's why this driver bit is colored orange. And if I'm cautious and accurate with my drilling of a very small but proper pilot hole, then I can remove this 6 or 10 times. Now I see a stress, some stress that took place in the part up here at the top. Now this is where it should be, but I wish it wasn't discolored like that. That's not a good sign. Okay, the function of this bracket, the bracket is not bi-directional. You cannot flip it this way and also use it. This way it will fall out, this way it won't. What we have is, I treated this 2 sides as a seat for the aluminum. Then this lip says my seat will stop precisely there to control the position, but this is not encountering a force that makes the aluminum is not being tugged in this direction. So that seat doesn't need to be very strong. And then, all right, to slide it in, we're putting it here, and then when we tilt, and that's when we have the compliant action taking place. And it has to tilt up temporarily, and then it tilts. It should nearly come back down to exactly straight. Well, design intent-wise, this should be perfectly flat, but it's still up just a little. So printing deviations, I think the overbuild has this just under a tiny bit of stress all the time, and it should be almost 0. But this making it 0 gives you the possibility of making it less than 0. It means having a gap, and that would be a worse condition than having this stress here. So when the beam gets put to use, I have a stick coming out here. So there's a stick mounted there. Oh, does that fit? No. And then we're tugging down on the right hand. And when we tug down, the ordinary mounted item on the wall is just pushing down in this direction, right? So that's what gravity's doing. It's pushing down, but also it is twisting. The beam out here plus gravity on a lever is making it want to twist like that. And so when you look in the last macro, the twisting, if this was free to twist and we eliminated that beam, then it would twist, it would roll out like that. And so effectively, the more weight that is hung on the outside here, the more this is going to try to roll. And that's what that arm's job is, simply to prevent the rolling. And it's not preventing the rolling. It's not supposed to prevent the rolling by squeezing down here, only by having this little hook. Therefore, the intended stress on this arm thing is only tension. And the plastic, any of the materials that you 3D print with, they would be able to withstand quite a lot of direct, straightforward tension in this. So if you were to draw with a Sharpie on the part, which direction is the main force, the load or the stress on the part during all times of the installation, like continually, then that direction would be this. It would be tension in that direction. So with that, we have a lot of, we don't need a strong member because the plastic can tolerate that very easily. But I think just during a couple of the installations, there were a couple of occasions where I tilted that up too high, and that's probably what caused it to get overstressed here like that. Countermeasure would be maybe extend the length of that beam so that it can lift a little bit higher and without with a lower percentage of deflection per length. That may be too technical. This bracket could be a demonstration. See, the very last snap is when this bottom corner passes the hump. I could make probably a video to treat this part as a compliant design example and then talk through that more deeply. But that's all for now for this video. Okay, so we covered the inclusion of steel rods, the simple bracket wall mounted. Now the rag chute, let's cover that. Before you can have chutes and ladders, you got to have chutes. No, that's not the line that belongs there. This is a dispensary, a chute for the rags, the new standardized rags, and it should be that I can easily access this to wash things or to grab one and operate in the lab. They're blue instead of white, so that these can do dirtier jobs, get stained, and they look like they belong in the lab rather than in a kitchen or something. So I just was checking that this Acro bin is amazing. There's several bins from Acro Mills and competitors that can be used in many ways based on the features that they have available. And this is version 2 of the chute. It was never meant to be a big project. All I did was take a piece of nylon or polypropylene, whatever this clear plastic is made of. It comes from the Plano bins, those dividers. I have lots of spares. I slid those into the slots of the bin, and now this goes here. It's just a piece of paperboard, card paper, whatever. Last night I just snipped this up into the shape that I wanted. It pushes here and has a datum, so I can cover up this bin, but the side of the bin I can still see how much is remaining here. That's great. Do I need to run a load of the laundry of these rags? Can access these. I can change that shape at will, and I can rebuild this paper thing out of something more robust in the long term. Cool feature of this is that there's already a CAD model of the bin. So these bins that are industrial grade, well engineered, and have sold in high volume globally, we can basically treat them like open source parts. So if I design a rag chute and I publish that online, more than half of the work is already done because the design of this is open source. That's the concept. That's how can we do wonderful expansion of open source hardware? The answer is use the things that are already open source hardware and then integrate. Minimize the amount of design that we have to do as individuals to create a new thing. And then we have a lot of engineering went into that. Here is one of the sisters of that product. And because of the high volume, some of these bins can be as much as $10 for this size. Kind of crazy. But this one, $267. On Grainger, you'll find a slightly higher price. You need to have an account, and a small discount gets us $2.67 for this. And that's going to be available for years and years to come. So it's worth making a CAD model for an accessory for this because we can trust it'll still be there. And then it'll be here in different colors. It's available in different places, and it has some amount of warranty and customer support, all that stuff that we can't get if we fully develop things from scratch. And so those are assets. This one is called a shelf bin. There are two large categories. The shelf bin is one, and the stackable bins are another. for the same size, the stackable bins cost more. It's more more mass of plastic per part, and they're structurally heavier. This one's intended for when you already have a shelf and you want to access something. And so, but it has this wonderful feature where there's a hook geometry on the back. So if you're retrieving this and it's tilting out from a long area, it is designed to tolerate the 20-pound rated load of this. If you were to come out here, perhaps say that you made a structure that does not have all the supporting structure all around this, and it just has a shelf made of beams or something like this rod. Okay, this is designed to support the whole 20 pounds in here as well, while it is resting only in this direction. That is part of their desired benefit to the customer, is that they can have it on a shelf and let it tilt out and it'll still hold up. Of course, these, so they have a label slot. If you want to have your own labels that are interchangeable on this, you can go and get these category number 7101 microscope slides. They're like $4 for all of these. They have a chamfered edge. They're made of glass, very visible, and it fits in there. So you can write on that with Sharpie on the inside, drop it in, and then you have a gorgeous shiny label, all interchangeable. Was it designed for that? Probably not. I will take credit for discovering that fitment. Let's see if they go in this one as well. Yeah. Not quite as good of a fit. So it depends on which model you get. And there's a competitor for acro bins at Grainger, something quantum storage systems. They do not fit with these. But anyway, I'm going to explore that more later. I just like to play with small pieces of glass. Seems like there's a lot of stuff you can do with that. Okay, that was rag chute number 2. Rag chute number 1 is already retired because I built it a little bit experimentally. You can take a paper, cardboard type of material. This comes from, I can't remember where I sourced this, but it's darn near free. And then also textiles can be darn near free as well in this quantity. And this one has been rolled on. I wanted to know, can I laminate cardboard with a textile to drastically raise the strength and the durability if you were to scuff it or splash it or whatever. And so it worked out pretty great. I'm pleased with this enough to reuse the method in an occasion that calls for it. But you can see a little bit of the product there. This is a urethane glue, and that's the go-to high volume per cost, $5 for a 12 or 16 ounce tube. You deposit it there, spread it out, and then you can lay down fabric, and you probably have a permanent. This will last a really long time, but I might just discard it because I like the modularity of the other one better. It looks nicer. And then down at the end, you take your end of your fabric. You can fold it over and pin it and put a piece of stretching stuff. This is the solution for the problem of, well, I don't know while I'm building this how much tension I'll need or what size of a orifice I'll need for those rags to not fall out. And so, hey, let's make it adjustable. And that means if you design something like this, you can also have that designed for different weights and sizes of items to be pulled out. All I did was quickly jigsaw a bracket on here with a dovetail, but none of this is all quick stuff, not good to copy off of, because the dovetails have very popular sizes already established and geometries that it's better to copy a standard from the woodworking field. And all I did was just chop whatever I had. And so that would mount on the wall like so, only this, they both go down, right? Okay, yeah. Yeah, very rough cutting. By the time I was done with this, I just wanted to get the project out of the way. I didn't want to dedicate too much time to it. So that is the solution I'd go with if I didn't have the Acro bin. And that bin was about $6. So very reasonable. Of course, there's shipping associated with that. So, okay, so we did the introduction of the Acro bins, although there's lots more to talk about for that in the future. The cardboard rack design is next. So I needed a place to stash cardboard. We were getting a lot of boxes in from Grainger and Amazon, and sometimes that cardboard ought to be kept around to ship things out later or for projects for the material itself. In any case, the moment that you don't want to decide whether you're going to throw it out, or slice it up, or crush it, is the moment that you got to put it somewhere. So we might as well have a place to put it. I woke up one morning with a possible solution. This is the whole plan before I just went to go build. And the whole build wasn't so that I could have a perfect cardboard rack, but I could test out what I think will work nice given the hardware we have. The need that I had prior to building this was I want to be able to stack up the cardboard vertically instead of sitting it behind the shelf, behind the desk, whatever, just setting it places that doesn't have a designated place. All right, and of course it'll have to adjust over time. I don't want to build fixed slots because I could take up a long amount of space when I just have a few pieces or whatever. And then the force of the cardboard can't topple this, whatever beam is upright to hold the cardboard in there, it should not be able to move this way. So we take a hinge, we mount that hinge in a slotted position on one arm of the hinge. The other arm of the hinge goes on a 2x4. And so this is a really low cost way to get yourself a sliding upright thing, and I'll show you how it works. But basically the full project is built with one 8-foot 2x4. That's $3 to $5 for all the wood, no, most of the wood. It has 1x4s here. They match up in the width, and a piece of Unistrut steel strut channel. This is centimeters, 22 centimeters wide, 72 long. And this is literally the values you'll need if you want to cut it and copy my project, 64 centimeters in length. Okay. It goes like this. So you can push. It can't tolerate a ton of pushing. I haven't tried to break it, but it doesn't slide in this direction. If I go like that, yeah, it holds itself. That was basically as intended. The tolerances are not super tight, and it can wiggle, but it does its job. So these ones are fixed to the floor frame, and this one, if I need to slide it out, I can do that by hand without any tools. This Allen key is here so I can make adjustments in the first few days as I see how tight does this hardware need to be down on the bottom. So let's remove the cardboard and show how it works. This is a really approachable project for if you don't even have a 3D printer or anything. This is almost zero engineering on your end to copy this. Firstly, I should show that you can lift it with one hand and it all holds together. I think that's pretty cool. Now, let's zoom in a little bit on the part that makes it work. Okay, these door hinges, it's actually quite elegant because it has its own little buffer. When you hold it in your hand, you can feel this is squeak free. And so door hinge technology, these aren't super awesome engineering things, but they're graceful for the cost. This is in a pack of 2 or 3 under $10. You can find this from any vendor, from several different sizes, and they're all fairly standard and nice thick steel. And so the 3 holes are just narrow enough. I think this is a 3.5-inch most common household size door. 3.5-inch width of the plate, and the screws are just narrow enough that it won't split the wood. So simply 3 screws, fasten it on there. And then this, it's kind of like our drop-in nut. That these are the most common fasteners that go together with the, what do you call this? Unistrut. That comes out of the off-the-shelf hardware bin. That is the bin that is off the shelf. It does come in packs. It is backed by Industries, but it's not a simple M5, M6 type of just fastener. So they come in this configuration and a couple of others. One of them has a spring, essentially to retain its position. If you want to hold your rail vertical, then it won't fall down. And I just had a couple of them that I pulled out already. It may actually benefit the design to include this blue plastic. I'm not sure. This is all very brand new design, all the way from concept. And we have the screw that's in the plate. This is a 1/4 screw. So the most of the hardware is British units. The the hardware that goes together with the steel strut is often 1/4 or 1/2 okay, so that's what we have. And these are maybe 10 of them for $4 or something like that. Very affordable. And across this whole project, I found every one of these components I found in the scrap for free. This particular hinge I paid for, but in the past, you can collect these from spare parts because they're so abundant. Okay, so the nut has a groove on each side. Sorry. This groove gives us a little bit of space where the edge of the steel sits in here, and without tightening it all the way, but just nearly, just enough that it contacts, then you have a position where you're not freely spinning. This can't lose itself in the track. It's down below the rail, and you're just tightening it up until it just sits contacting that rail. And that's what lets us do this sliding action, but it doesn't come out mostly. It may be useful to add a nut and a thread lock so that a nut above between this space would hold its position. I'm just not quite sure yet. And now my brain's on the video rather than on the design details. But yeah, plenty of ways that this could be improved and made more consistent. But it's so simple, and I wanted to present to people the simplest variety of the design that I could come up with. So this will rotate. I've added a piece of plastic tape. This is wallpaper, but it's extremely low friction, and it has a nice thickness. Maybe it's 10 mil or something around there. 0.2, 0.1, not quite 0.1 millimeters, but thick enough that it should last a little while. And that will reduce my friction because the edge of in here has friction. The manufacturing is not flawless. And then on top of that, we have a thick type of galvanizing that just makes it coarse, and it feels, with your finger, does not feel like a sliding type of track. It's just shy of something that you desire for sliding directly on there. And so that's why the plastic is helpful. But it works even if you don't have the plastic layer. And then this goes in. You can tighten this by hand. I chose a screw that has a broad head so that since there's only one screw that's fighting all of this force, when I tilt this back, then can be quite a lot of force concentrated around the screw. And so a broad head helps. And the low profile head also helps me maintain a flat zone here where cardboard can slip on and off of there as needed. Yeah, I don't think I need to talk too much about all the details. This is something that that you can observe just directly, and you could try it out if you want, but it's cool. It works, and you could very much repeat this type of process. All the action is when this lifts, then you have an angle on the plate. The plate goes from flat to up, and that adds a lot of tension on the bolt. Clamp, it grabs its position in the slot, and it can't go anywhere. And so you could certainly build an item with a geometry just like this for the aluminum extrusions that we work with. And there's probably a lot of 3D printed ideas that could make a one-shot print for a sliding and stopping bracket. Now, if we zoom all the way out, this steel, this would not be a very achievable project without the steel, with only the wood, because we have a large amount of pressure on the very small region when it's doing its stopping action. But since you do have the steel, we can hold this vertical as well. And so you can create any inventions. I'm sure you could find benchmarks also that are more well worked out than my example. But you lift and drop it down, and then it's going to hold itself. And if you were to push and put weight on a shelf like this, you will not reach a point where you push down too far and then it slips. You will reach a point where you push down too far and something shears and something breaks here. So I'd love to see if anyone in the community has created something along these lines on my Discord or in the comments, or share links or videos. I'd like to see if this can be improved and if it can be forked out into other designs. This one's not digital. There's no digital content for this, except that you can download this hinge and this rail, of course, online. I have my own parametric copy of the design of this Unistrut. Final little details. This hinge is not necessary. It is serving a purpose right now of holding the wood together, but you could use any other method to hold that wood together. The vertical bonds to the horizontal with a fastener, and let's see if that's in frame. So these are screwed in, okay? But then to hold them together at just the right spacing, the spacing is slightly wider than the steel itself, and I've put a piece of cork in each of these. I'll show you that. That was a final touch for me. It will work without that, but I think if you take up the gaps in any kind of build like this, then you eliminate chances of pinching and shearing. You reduce forces that are unexpected whenever you're moving the equipment around. And speaking of gaps, the other solution is a paint stick here. I keep an inventory of a handful of these paint sticks, and they work as shims quite often. It seems almost precisely the thickness of this 1x4, which is not an inch. I think it's 3/4, plus the paint stirring stick equals the height of this this strut. So that means if you want your bracket to be strong and flush, then you can, one screw goes into this board, one screw into that board, and the final screw is just clamps down here. It's a hex 6mm. I think I just lost my little. I have the 6mm wrench around here. Anyway, don't want to belabor the video. One other tip you may want to copy. When I built this, then I know that I might need to adjust it, and I won't remember the size or the height. I want to keep the Allen key with this apparatus for a little while, so if I need to make adjustments, I can do it right there where this is. And so I grabbed one of my 4mm Allen keys, which these come from all different projects. Sometimes they're free add-ons that come with an appliance or something. And in here I have this magnet. I didn't tell the story of this build ever because I'm not sure if it's even reasonable to keep all of your Allen keys together. But the purpose it wound up serving for us is that you have more than you need. They don't need to be together because you don't ever need that many Allen keys. And the preferred tool is as someone else in the community mentioned, ball end driver type bits or the straight type bits that go into a driver like this. But if you keep them all together and you don't throw them away, then you wind up with a project that just might need an adjustment. You can grab one of those and then you don't need to track the inventory. It can stay together with the invention and it can stay there wherever it's needed. And you don't have to worry about taking one of your precious good drivers. If that gets lost, it's okay. So that is the cardboard rack. Now this can go just somewhere else besides in the middle of the lab for the short term and the long term. I'll decide, do I inventory this stuff or do I just recycle it every time right away? I definitely always break them down with the utility knife that lives right here. I just realized it may be misleading in regards to the beams that we're going to continue to pursue and expand on in Open Lab. Those will include the materials, the EMT, steel, soft steel conduit, and fiberglass rods, but those ones still have yet to be narrowed down as where they belong in regards to in between structures and electronics. So for example, this is more valuable for carrying wiring internally than for being a load-bearing structure. This one is more useful as an accessory or a strength-adding material for other structures. That's why I didn't list them initially, but those ones will still continue doing 3D prints and stuff like that allow us to integrate. Oh goodness, there's two topics I didn't touch on yet. One is stitching. I'll cover briefly and I'll present to you my problem statement and another problem statement about spools for dispenser. I have a halfway universal spool now to be built that will help clean up the wires, but it doesn't answer the other needs that I have, and maybe you can help. So we have the heavy cables that really don't belong in a bin. As long as they're here, they ought to be retrievable. It doesn't cost us anything as far as the volume taken up in the lab to make this stuff retrievable. We can use a drill. Now, I've demonstrated this in a short video. A drill can be inserted here to, in the green part, to spin the spool, and then you can easily, with one person, wrap up any of the wires that you had. Mainly for me, this is for larger inventoried cables that I may want to have half a meter. I want to pull it off and snip it, use it in a project. Not so much for like USB cables and whatnot. So cables that are tools themselves, they don't go on spools, but the cables that are supplies, that are materials that are consumable, those belong on spools. And I have a large one and a small one as well. So some of these different manufacturer spools, they're good quality, but they're not uniform. And since they're not uniform, we can't just design our own rack. Let's say if I want to have all these hanging, the camera. If I want all of them hanging in a row here so I can pull at it and snip a piece, there's no need for it to be tucked away in a drawer. We just don't have the uniformity to get us there yet. And then, what was it? Well, in any case, those are not the only things, wires are not the only things to get spooled. This sandpaper is, I have many abrasives, and this one is used all the time. It's cheap enough that you can just pull out a foot of it and snip it and use that. Like, for example, I did that when I was quickly throwing this together. I didn't use a methodical process to take the edge, the burr off of here. I just grabbed a piece of that, and I'll continue to do this until I have specialized tools for smoothing rods and things like that. So in the meantime, short-term solution was, hey, well, let's label these because it's really hard to tell by feel, and they're not labeled in a way that you can see them. And yeah, I flipped this upside down because it didn't work very well the other way. Anyway, so if each one of these has its own clip, then it won't fall back in. It's a pain when it falls back in. But what would be great is if I took my two favorite grits, a low grit and a smoother grit, and I had my own dispenser. And I was thinking, well, now that we have control of the geometry of the spool, we could make a dispenser. We could stick that inside of something like a low cost $2.50 box like this one, or even the hexagon. Yeah, the hexagon. 3D print an adapter that has a nice, neat outlet for one of those rolls. So we drop the roll in on our own spool. We can use the drill. There's a cover and we can rewind it, but I want it to snip. I want to snip with one hand. I want to retrieve some amount and snip it off with just a blade on a spring or something like this. That could be so much easier, and it's used so frequently. I do recommend that you buy not a particular brand, but any type of. Having this paper on cloth is so much advantageous, so advantageous compared with the paper, sandpaper, because it doesn't tear while you're using it. So for multidisciplinary purposes, this, if you could only have one, I would take the cloth spools over the paper sheets for sure. 5 years, this hasn't run out yet, but having a dispenser would help a whole lot. And if that dispenser internal module is suitable to say, oh, I don't want to have 5 dispensers, then we could have that internal spool still fit straight onto a long center hub. And all the decisions can be up to the user. How cool is that? So building these spools caused me to discover friction welding. And so first I was gluing one of these to this adapter to the PVC, but the edge is not straight. And it's really hard to get it perfectly straight and square, which is necessary if you're going to glue just that face. And then I found out of frustration that if I just spin this hard and look at this interface, I wonder if we can get the focus. Yep, now it's glued. Oh man, I did that one a little bit harder. Had my tiger gloves on, so I wasn't afraid. Anyway, so now this is locked together. The ABS and the PVC essentially friction welded, and all the deviations on your cut no longer matter. So I think that's super cool. It saved me a lot of time to make a bunch of spools. Yeah, you could trim that off if you want to. Anyway, yeah, this design is free. Now it's online, 2 different sizes, and you can, I think, do a lot with it because this PVC is very long piece for like $2.50. So it's just darn near free. And yeah, I would love to find out that somebody was willing to try out designing a dispenser. Okay, the final topic that I'm not going to fully cover is stitching. Textiles are really important. We cannot engineer everything.